In 1940, the Tacoma Narrows Bridge stood as a modern marvel. Its slender, elegant design connected two shores, embodying progress and ambition. Yet, this seemingly perfect structure harbored a fatal flaw, one that would soon redefine engineering principles forever. The Tacoma Narrows presented a formidable challenge. Strong currents and deep waters separated Tacoma from the Olympic Peninsula, hindering economic growth. A bridge was desperately needed to connect these vital regions, promising prosperity and easier travel. Engineers envisioned a bridge of unprecedented slenderness. The design, led by Leopold H. Ammon, prioritized aesthetics and cost efficiency. Its narrow deck and solid plate girders were considered innovative, creating a graceful, minimalist profile across the water. Construction began in 1938, a monumental undertaking during the Great Depression. Workers toiled tirelessly, erecting the towering steel supports and spinning the main cables. This ambitious project brought jobs and hope to the region during challenging economic times. The bridge's towers were remarkably slender, a defining characteristic of its modern design. These elegant structures supported the main cables, contributing to the bridge's light and airy appearance. They were a testament to the era's forward-thinking architectural trends. Unlike traditional bridges with open trusswork, the Tacoma Narrows Bridge used solid plate girders for its deck. This innovative choice offered a sleek aesthetic and simplified construction. However, it inadvertently created an aerodynamic shape, trapping wind energy beneath the structure. Even before its official opening, the bridge earned a peculiar nickname, Galloping Gertie. In even moderate winds, the deck displayed a noticeable vertical undulation. While initially a curiosity, this early movement hinted at deeper, unforeseen engineering challenges. On July 1, 1940, the bridge officially opened to great fanfare. Thousands flocked to witness this engineering marvel, eager to drive across the new connection. The atmosphere was celebratory, brimming with pride for this bold symbol of regional progress and connectivity. Soon after opening, the bridge's peculiar movements became more pronounced. Drivers reported a distinct up and down motion, even in light breezes. This phenomenon, while unnerving, was largely dismissed as a minor quirk, part of the bridge's unique character. The bridge's galloping became a local attraction. Some thrill-seekers intentionally drove onto the bridge to experience the unique ride. This public fascination, however, masked growing concerns among engineers about the structure's unusual and persistent behavior. Behind the scenes, serious concerns mounted. Engineers struggled to understand the cause of the oscillations, attempting various dampening solutions. Cables were installed to tie the deck to the ground, but these efforts proved largely ineffective against the bridge's inherent instability. Professor F. B. Farquharson, an expert in aeroelasticity, was called to investigate. He began a detailed study, documenting the bridge's behavior and attempting to find a scientific explanation. His work would become crucial in understanding the disaster's true nature. To better understand the bridge's response to wind, scale models were tested in wind tunnels. These experiments aimed to simulate the aerodynamic forces at play. Early results were perplexing, as the unique design reacted unpredictably to varying wind conditions. November 7, 1940, began like any other day. A moderate wind, around 42 miles per hour, was blowing through the Narrows. No one anticipated that this particular wind speed, combined with the bridge's unique design, would trigger its catastrophic final dance. As the morning progressed, the oscillations grew violent. The vertical waves became more extreme, making passage treacherous. Drivers abandoned their cars, fleeing the increasingly dangerous structure. The bridge was no longer merely galloping, it was fighting for survival. Suddenly, the bridge's movement shifted from vertical to terrifying torsional waves. The entire deck began to twist, one edge rising 28 feet while the other simultaneously plunged. This unprecedented motion indicated a fundamental structural failure was imminent. Amidst the chaos, Professor Farquharson remained, meticulously filming the bridge's final moments. His footage, though harrowing, became invaluable evidence. He risked his life to capture the scientific data needed to understand this unprecedented structural failure. From the safety of the shore, thousands watched in stunned silence. The majestic bridge, once a symbol of pride, was tearing itself apart. The scene was surreal, a terrifying ballet of steel and concrete succumbing to the invisible forces of the wind. One brave reporter, Leonard Coatsworth, abandoned his car and fled the collapsing span. His desperate escape left behind his vehicle and beloved dog, Tubby. This personal account underscored the sheer terror of being caught on the bridge during its final throes. With a deafening roar, the first sections of the deck ripped free. Concrete slabs and twisted steel plunged into the narrows, sending plumes of spray into the air. The bridge was no longer merely twisting, it was actively disintegrating, piece by agonizing piece. Then, the main span gave way. The central section twisted, buckled, and tore itself from the support cables. In a matter of minutes, the proud structure collapsed entirely, plunging into the waters of Puget Sound. The Galloping Gertie was no more. The morning after revealed a scene of utter devastation. Twisted girders and broken concrete littered the Narrows, a grim monument to engineering hubris. The once elegant bridge was now a submerged graveyard of steel, a stark reminder of nature's power. An immediate, extensive investigation began. Leading engineers and scientists painstakingly analyzed the failure, seeking to understand the complex aerodynamic forces at play. The collapse was not due to structural weakness, but rather to aeroelastic flutter, a phenomenon poorly understood at the time. The Tacoma Narrows disaster became a pivotal case study. It revolutionized bridge design, emphasizing aerodynamic stability over mere static strength. Future bridges incorporated open trusses and stiffer decks, ensuring wind could pass through, preventing similar catastrophic failures. The collapse of the Galloping Gertie remains a powerful lesson in engineering history. It taught humanity humility in the face of nature and the critical importance of understanding dynamic forces. Its legacy lives on, ensuring safer, more resilient structures for generations to come.